So hello, good afternoon everyone, or maybe I should say good morning or good evening, depending on your time zone. My name is Ioannis Zotos, and I would like to thank you for being present in this web seminar about vibrations in KISSsoft. My presentation will consist of some slides and also some view of how you can handle vibrations in KISSsoft and KISSes. So going to the contents of the presentation, I'm going to start with some motivation behind. So what is the reason of calculating vibrations from on the first hand? I'm going to define what dynamic calculation is and some basic equations there. Then I'm going to talk about model analysis and forced response. Give some overview about validation we used and the literature used to develop our software. We're going to talk also about excitation frequencies and briefly give you an overview of interfaces to other vibration software. Before moving further, I would just like to inform you that there is always an option to ask questions if you want. At the end of this session, I will try to answer as many as possible. Those that are unanswered, I will just email back to you with an answer. And also in the download section of this webinar tool, you can find this presentation and also a list of licenses or modules of KISSsoft and KISSes that you can use to calculate vibrations. So the motivation of calculating dynamics on the first place is, of course, it is that the world is not static. Dynamics is a very important part of, or should be a very important part of any design work, because dynamic loads can really cause damages. There can be overloads due to resonance, and we should avoid any resonance situations where the operating speed is close to the resonance frequency of the structure. Further than that, vibrations can cause noise. And there is an increasing demand of reducing noise, for example, in noise-sensitive applications, for example, in electric vehicles. So all that, including NVHs, are very strong motivations to have a good dynamic analysis tool at hand when designing. Starting, let's try to define what is a resonance. In this respect, a YouTube video could help us a lot in order to see, in order to visualize what resonance is in a very simple example. I will just start this YouTube video for you. So you see here, sorry, I'll just go a little bit back. So you see here, we start with an excitation frequency. We have a dynamic force at this end of the structure, exciting the structure in a specific frequency, and depending on if it is this exciting frequency is below, equal, or above the eigenfrequency, the whole thing behaves differently. So in this first part, the eigenfrequency or the forcing frequency is below the eigenfrequency. So we saw a very small movement, very small response of the whole structure. When we are exactly at the eigenfrequency, we see that even though the forcing frequency is constant, the whole system is vibrating violently, and we can see that this is where the resonance appears and have a very big amplitude of the vibration in the end. And this is a supercritical case where the forcing frequency is above the eigenfrequency. Again, the response is lower, and we can also see with this yellow and pink marks, we can see also the phase difference between the input and the output. So we could also follow how the input is with respect to the output as far as phase is concerned. So keeping in mind that the designer should know the eigenfrequencies of the structure of the system he's designing, and make sure that they don't coincide with the exciting frequencies. So the eigenfrequencies are actually properties of the system itself. The eigenfrequencies depend on the mass, stiffness, and the boundary conditions present, whereas the exciting frequencies depend on the operating speed, the number of teeth in a gear, and so on and so forth. So these two properties of the structure, the user should know. Regarding noise and NVH, as I described previously, this is also a very important aspect of a very important motivation behind calculating vibrations. So what is really happening is the whole gearbox, as shown in this case, is vibrating, and this vibration is transferred to the housing of the gearbox, and the vibration of the housing is the one that is exciting the molecules of the air. Then this is perceived as noise or as sound, as noise at the ear of the receiver. So the whole thing is, in order to be able to analyze noise, we should first of all analyze vibrations in order to know how are the exciting forces and frequencies on the housing that in the end generate this noise. I will just show very simple equations today, just to so in order to understand the same language. So the eigenfrequency of a spring and mass system, a very simple system, is given by this equation. As I said, it's a property of the structure, and depends on mass, stiffness, and the boundary conditions of the structure. Whereas for the forced response, the force vibration gives us actually the response of the structure and the dynamic force. In this case, also damping comes into play, since this affects the dynamic response in the end. Here you can also see the designation of what we use for stiffness, damping, and mass, what symbols we use for stiffness, damping, and mass. And so this is the main difference between eigenfrequency calculation and forced vibration calculation. So in the eigenfrequency calculation, we calculate the property of the structure that is called eigenfrequency, and gives us a frequency that we should avoid exciting during operation. Whereas in the forced vibration, we calculate the exact response of the structure due to a dynamic excitation, due to dynamically excited force. Going one step further to model analysis, that just to describe a bit more what is included in there. As I said, mass and stiffness is needed. What is mass in a gearbox analysis? It's clear. It's the mass of all components. What is stiffness is something that's a bit trickier most of the times. So stiffness includes elasticity of all parts. So bending stiffness, torsion stiffness, axial stiffness of the shafts themselves. It also includes stiffness of the bearings and supports, being it rolling element bearings or sliding bearings. And this part is quite demanding computationally, so we get the correct stiffness value there. And also, if we are talking about a system of shafts, we also need to take into account any connections. For example, due to the gear mesh stiffness. So this is another stiffness that comes into play in systems. And then we talk about coupled vibrations between shafts. What is important at this point is to point out that whenever we are talking about system of shafts, we should always analyze them as a system. It's not enough to just analyze a single shaft and then try to derive results of the dynamics of the full system of shafts. So a system of shafts should be analyzed as a system, since the gear mesh stiffness is a very important coupling factor in there. I will just stop presenting now and just go on to showing this all in KISSsoft and KISSes, just with 2 examples. So I will start with KISSsoft. Just started Soft example 9. This is one of the examples that we provide with the software. And any test version has them also. Here you see a coaxial Soft system where we, in this basic data input, we have defined that we want to calculate the bearings with inner geometry. So every bearing, every support, and every connection between the shafts is calculated with inner geometry, and the exact stiffness of them are taken into account. Then we just go and ask for how many eigenfrequencies we want KISSsoft to calculate. And then we move on with the calculation. It's a quite fast calculation, and the whole stiffness of the structure is taken into account. Regarding the results, we have results in the results window where we see all the eigenfrequencies as values. So these are the eigenfrequencies of this coaxial subsystem. And we can also get more information from graphics. So we go to the 3D display first, where we can see the whole shaft vibrating. Here we can get a first view of how the whole system is vibrating through an animation. So you can have a look of every vibration mode. So this is a shape this is a mode shape that the shaft would take if it would vibrate in one of these eigenfrequencies. If you see this is mainly an axial vibration, but at the same time there is also a bending component there. So since we are using the internal geometry bearings, vibrations are coupled in all directions. We can go through all eigen modes and see how the system is vibrating. We can even change the scaling so we can see them more clear. So for every eigenfrequency, we can have a 3D view of the eigenmode, and we can see the behavior of our structure, of our system of shafts in every one of these eigenfrequencies. This is quite useful in order to get a better feeling of how our shaft is going to vibrate in every eigenfrequency. Sometimes it's even, if we want to have more details of its eigenmode, it's better if we go and see them in a 2D plot. Here we can also see the nodes and antinodes of its eigenmode. So here again we can go through all eigenfrequencies and have a view of all shafts in the shaft system and how they vibrate. We can have the mode shape better represented on a 2D plot, so we can see in every exact position of the shaft how the mode shape looks like. I'm talking all the time about mode shapes. We should keep in mind that these are not real responses of the structure. These are normalized displacements, so this is just giving the shape of the structure for each of these eigenfrequencies. The exact response of the structure is calculated through a forced response analysis, as we said. So it's not just the modes of vibration that we're taking from the eigenfrequency analysis. Another useful thing from the eigenfrequency calculation in KISSsoft is a special report of nodal points. So with nodal points meaning points where the eigenmode crosses a zero axis, and these are most of the times quite quite detrimental, can be quite detrimental, because we know that, for example, if we have a bearing on a node position that cannot take any tilting, then this bearing will have a hard time there, and probably we will have a failure at this component. So we have a very detailed report here with all the nodal points of its mode shape. Going further, I will just go also to show you how the whole eigenfrequency calculation analysis can work also in KISSes. So in this case, we have a simple two-stage helical gearbox, and we want to calculate the eigenfrequencies of this full system. So we're talking about coupled eigenfrequencies, so not each shaft separately, but all of them together as a system. For that, we need this subsystem analysis calculation tool that is available in KISSes. And then we ask for the model analysis here. Here we can ask again for a specific number of eigenfrequencies that we want from the calculation. There is another input here, since gear meshing stiffness is also taken into account in case of subsystems. We can define how the meshing stiffness should be calculated. So it can be either calculated using ISO and then held constant, or we can use our contact analysis tool and have a more accurate calculation of the meshing stiffness, but also a more time-consuming one. There are also some two extreme cases, having infinite meshing stiffness or not take meshing stiffness into account at all. For this case, I will just go with the ISO calculation. There is also the option to calculate only torsional vibrations. So if we don't want the fully coupled vibrations analyzed, but we are interested only in torsional vibrations for a reason, then you can go and calculate only the torsional vibrations. For this demo, I will just calculate the full coupled vibrations, so you can see how the whole system is behaving in every eigenfrequency. As you see, it is a quite fast calculation, and we get a display of the whole subsystem in 3D again, so we can have again an animation of how the whole system is vibrating. Here we have a list of all eigenfrequencies calculated, and then you can again play a movie and see the animation of the whole subsystem. For example, in this case, we see that this shaft is having mainly an axial vibration, or the energy of the axial vibration in this case, in this shaft, is higher, but due to the coupling between the shafts, due to the gears and the helix angle of the gears, this axial vibration is transformed to a torsional vibration in the two other shafts, and we cannot see it very clearly, but also an axial component in these two shafts. So we can see how the whole system is vibrating and how the vibrations are coupled. Similarly, we can go and see all mode shapes for different eigenfrequencies in this system. In every case, we see that the whole eigenfrequencies are fully coupled. We can also see some cases where there is a movement between two gears in this case. So this means that this vibration mode is mainly controlled by the gear meshing stiffness of these two gear pairs, and there is no much energy going through these two gears. Apart from this plot, from this 3D animation, there is also a bunch of data available under this model analysis results table, where we have the exact mode shape values for every shaft in every eigenfrequency of the system. So somebody can just grab this data and select his own favorite plotting tool, for example Excel, and paste the data there, and then have a more thorough look of the mode shapes and of this system. Talking about eigenfrequencies, there is also another term that we should have in mind, another analysis that can be performed, what is called the Campbell diagram. For that, I will just open another KISSsoft example. So we have calculated our eigenfrequencies, but there are cases where if we have big gyroscopic effects involved, so we have big polar moments of inertia on our shaft in a position, so for example in a ventilator or similar cases, there can be cases where the eigenfrequencies depend also on the running speed of the shaft. So in order to analyze cases like that, we should calculate eigenfrequencies through a speed range of the shaft. For that, I just use a very simple Jeffcoat rotor example. This is kind of textbook case, and this can be used to see how the whole thing is vibrating and how what is the idea behind this Campbell diagram calculation. So here we have two shafts. This center one has a big polar moment of inertia and it is rotating, and we want to see how the vibration is affected. The vibration eigenfrequency is affected by the polar moment of inertia, by the speed of this shaft. In order to achieve that, we should remember that we have to take into account the gyroscopic effects. These are the effects actually that are stiffening our shaft. And so the gyroscopic moment is trying to bring the shaft back to the neutral position and then is stiffening the shaft somehow. In order to calculate that, we need a special calculation tab called Campbell diagram. There we have to define a speed range where the controlling shaft will take any of these speeds based on the number of calculation steps set here. And we can also define how many resonance curves we want to have in the resulting plot. So go on and calculating this Campbell diagram analysis. So what is happening in the background, the shaft, the disk in this case, is taking all the speeds in this speed range, and eigenfrequencies are calculated for every of this, for all these speeds. Then you can go into the shaft graphics and see how the Campbell diagram looks like. We can see that in this case, apart from an eigenfrequency that stays constant, so it is not affected, or it's there is very low effect of the gyroscopic effect in this eigenfrequency. There are two eigenfrequencies that have a very big effect, where the of the polar mass moment of inertia. And here we can see that, for example, that this eigenfrequency has a forward whirl, so the eigenfrequency is getting higher as the speed of the shaft is getting higher, and this is a backward whirl where the eigenfrequency is getting lower as the speed of the controlling shaft gets higher. Here we also see the current running speed with this black dotted line. We can also see the resonance curve we asked about. So this is once per revolution resonance curve on the plot. And we can also see the crossing points between this 1 per revolution curve and the eigenfrequencies. So from this we can see which eigenfrequencies are excited for every 1 per revolution input of the running shaft. So all in all, we can, using KISSsoft and KISSes, we can have a very deep view on the model analysis of single shafts and shaft systems, and also gyroscopic effects through Campbell diagram calculation in shafts and shaft systems. Going back to the presentation now. I'm going to talk briefly about force vibration, so I'm going to move to the second subject, the second main subject of this presentation. So force vibration is actually the calculation of dynamic response of a structure due to dynamic force, dynamic excitation force. This is the simplest equation describing this response in a simple mass damper stiffness system. With this equation, we can briefly understand how the structure is vibrating for different vibrating frequencies. So for example, we can see that when omega, when this frequency is low, then the response of the structure is mainly affected by the stiffness. So we have what is called the stiffness control region of the response. At high frequencies, it's the mass that is mainly controlling the response of the structure. So it's the mass control region at this area. And very close to the critical speed, or at the critical speed, there is it's the damping that mainly controls the response due to the phase shift between input and output. So we can have a quantitative qualitative way of describing how the response is changing for every frequency range. In order to calculate the dynamic response, we need some additional data. These are, of course, the dynamic forces that are used to excite the structure. This can be an unbalanced mass or a transmission error in a gear pair or any other thing like that. We are going to see dynamic forces, excitation forces later on in this presentation. You also need damping values for bearings and materials if available. And you also need some evaluation points, so we have to define some points on the structure where we want to calculate the response of the structure. For that, I'm going to go back again to the software and show you briefly how this all can be done in KISSsoft. For that reason, I'm going to use again the same example that I used for the dynamic analysis. We see in this case, let me make some more space in this window. We see that in this case we have defined two locations at these two bearings where we want to calculate the response of the structure. So this can be thought as like measuring probes that we have attached on the structure. And we have also defined our excitation force in this case is an eccentric mass, is an unbalanced mass at this coupling position. This eccentric mass is defining just the eccentric part of the mass, so not the total mass, but just the eccentric part of that. So it's an eccentric mass of 10 grams with an eccentricity of 5 millimeters. In order to run this calculation, we want this special calculation called force response. In this case, similar to the Campbell diagram calculation, we have to define a speed range. So this is the range of running speeds of the shaft that we want to see how the whole shaft system is responding. We define also how many steps we want to calculate in this speed range. We have defined a rather high value in here, so we want to have a good resolution close to the eigenfrequency. And we can also define damping of the material. This is the hysteretic damping that can be used to take into account material damping in the structure. Further than that, we also there is an option to define damping in our bearings and supports. So through this stiffness and damping, so for every bearing and every connection or support, we can define damping values that will be used for the calculation of the dynamic response. So after all this data are input, we can go and calculate the dynamic response of the structure. So the software is calculating the excitation force due to this unbalanced mass for every running speed. and then it calculates all response quantities of the structure. Contrary to the eigenfrequency analysis, in this case we don't have any eigenfrequencies calculated, but we have what is called the resonance speeds. So we have the speeds where we have resonance, so where we have the highest amplitude of vibration. And in this results window we see the large half-axis of the response ellipse. So it's actually the deformation or displacement response of the structure at these resonance speeds. We can also use again a graphic to see this response, and we have a rather common view of response of dynamic response of the system. We can see here the peaks are the resonances, and you can define, for example, here which of the two measuring points we want to plot. There are different things we can plot, so there is a lot of information available regarding the dynamic response, displacement, torques, forces, and for every of them we have also amplitudes or components in every direction, so we can have a very deep view of the dynamic response of the whole structure. In a similar way, we can work in KISSes, and we can calculate the dynamic response, unbalanced response, or the dynamic response due to unbalance of this system. For example, this is again an example given out with together with KISSes. This is a 4-speed transmission gearbox example, where we have defined an unbalanced mass in one of the shafts, and we can again calculate forced response. Right-clicking again on the same subsystems analysis calculation, we can go and ask for a forced response. In this case, we have similar inputs like we have for in the case of KISSsoft. So speed, range, number of points, and hysteretic damping. But as it was the case with the model analysis, we also have the option to take into account the meshing stiffness. So this is the extra stiffness we have when we are talking about subsystems. And we have again the same options like in the model analysis, either from ISO or from contact analysis, or the two extreme cases, infinite or 0. So what this calculation is doing in the background is first of all doing a kinematic analysis of the whole gearbox based on the speed range set by the user. So the KISSes is automatically taking every one of these speeds in the speed range and applies it on the control shaft, and then performs a full kinematic calculation of the whole system. Maybe this is not so important, or maybe the importance of that is not so clear in this simple example, but you can imagine if we have a very complicated KISSes model where we have, for example, user-defined kinematic conditions, then KISSes is taking into account all the inputs for the kinematics, and then it makes sure that all shafts has the correct speed for every speed of the controlling shaft. So having calculated all speeds during this kinematic calculation, KISSes is calculating then dynamic excitation, so the dynamic force due to the unbalanced mass, or the unbalanced mass is defined, and then from that it calculates the response, the forced response of the whole structure. What we get as a result is a plot of the force in a predefined point, in a point that we have defined when asking for this forced response calculation. And we have much more information in this results table, again, where we have every available information for every measuring position defined in every shaft on the system. So in every shaft of the shaft system in KISSsoft, we can define again a measuring point. So we can set probes at different locations in any shaft, and then in this results table we get all the resulting response data for every documentation point. Here, for example, we see that for every speed we have many information like amplitudes and forces, and so there is plenty of information available in this plot, in this data, and somebody can really extract as much information as necessary out of that. Going back to the presentation again, I'm going to just give a brief view of the literature that was used during the implementation of these tools. So I just give here two references. There were many more used, and papers and internal developed theories. And so you can see it was matrix methods in elastomechanics was one of the books mainly used to derive the mathematics of the methods. You can also see this machine dynamic book of Kremer. Regarding validation, some parts of the validation were done in a very early stage using very simple models through textbook cases using this book of Blevins. And then, as it's always the case with the development of dynamic analysis software, we were based on other specialized software based on samples from industrial applications, so more complex and more realistic examples. It's always the case that when developing vibration analysis software, not much experimental data are available. So most of the times, everybody is trying to be based on and validate his results compared to other specialized software. This is also what we did. Moving further, I told you in the beginning that there is one part is the eigenfrequencies of the system, what we do with the model analysis, and then another thing we should take into account is calculation of the excitation frequencies. So what frequencies are exciting the system in the end. These excitation frequencies can be also calculated inside KISSes. And for example, for gear meshes, they depend on the number of teeth and the running speed. For rolling bearings, they have these classic frequencies that we use also to identify any faults in the bearings, BPFE, BPFO, and the rest. All these frequencies can be calculated inside KISSes. I will just show you how in a simple example. So for that, I go back again to this 4-speed transmission gearbox, and we have to import this frequency table in there, and right-clicking on bearing or meshing frequencies, we can get the frequencies and a specific number of harmonics of them. All of the frequencies calculated are also exported in a CSV file in the location of where the KISSes file is saved. So we export the bearing frequencies and also the meshing frequencies with a specified number of harmonics. And we can see them in the CSV files and also in these two tables of KISSsoft. We can see all of the exciting frequencies, and based on that we can see if any of these frequencies are close to our eigenfrequencies. That way we can see if we have any potential issue of resonance. Going back to the presentation, I'm going to talk briefly about interfaces to other vibration software that are available through KISSsoft Kisses. So as you saw, KISSsoft and Kisses can be used extensively for the initial stages of the dynamic analysis of shafts and shaft systems. But of course, if somebody wants to go deeper into more exact or analysis in the time domain or any other more advanced dynamic analysis, it would be better if somebody would select any of the specialized software, dynamic analysis software for these cases. For that reason, there are interfaces to this kind of software, either through a general XML export. So every Kisses model can be written as an XML file, including shafts, gears, bearings, data, stiffnesses, positions, everything. So all of that can be saved in an XML file and then read in from another software. But there are also interfaces, direct interfaces to some specific software, like the ones shown in this slide, AVL, FEV, Recordine, MSC. There is also a planning for interfaces to more specialized vibration analysis software like Simulia or GT Suite. And of course, there can be other interfaces developed on request. At this point, I would like to thank you for your attention during this presentation. And I will take this opportunity to remind you that we will be in Hanover Fair next week. Here you can see the whole number and the stand number where you can find us. Many engineers from KISSsoft will be there, and there will be available to discuss with you any issues regarding vibrations or any other issues that may be of your interest. At this point, if you have any questions, I will be happy to answer them. Let me check if there are any questions. Okay. So one of the questions is if KISSsoft has the bearing properties of the bearings in the bearings catalog. Actually, this is a big question that nobody can really answer, because damping is a value that is depends on many factors, and it's not, most of the times it's not available in a catalog. It depends on the lubrication, on the lubricant, on the lubrication conditions, and many other things. So we don't have any damping values from in the bearing database or something. So the damping values is something that has to be input by the user. Another question is, there is an option of speed-dependent roller bearing stiffness. This is the case where, due to the, we can take into account the position of the shaft at different running speeds and how this affects the bearing stiffness. This is a rather sophisticated way of analyzing the stiffness. Most of the times, for the analysis that are necessary at these initial stages of dynamic analysis, a constant stiffness is enough, but somebody can also take that into account. So the speed-dependent roller bearing stiffness means that the stiffness is updated for every running speed. So if there is effect of the speed on the stiffness in any of the bearings, then this is taken into account. Another question is if we run the kinematic analysis for every step in the speed range, or if we just extrapolate the currently known kinematic condition. Now we do a fully kinematic analysis for every step in the speed range. This makes the whole calculation a bit slower, but then we are sure that we take into account correctly all the user-defined kinematic conditions. There is another question if we can implement internal damping, for example, friction between loose interference fitted parts and shafts. There is no element like that available at the moment in KISSsoft. This would require a new element, a new kind of force element necessary. If this kind of friction, and I know that this is not the case, but if somebody could approximate this kind of friction with a viscous kind of damping, then somebody could just add general support at the position he wants to take into account this damping, having zero stiffness and just a damping value in there. This could be a workaround, but yet again, this would be taken into account as a viscous damping. I think this is not the best solution for this problem. Another question is what is meant by the P column in the meshing frequencies in KISSes. This is the power of a specific gear pair that is shown in this table. Then there is another question if we have any real examples of how somebody could solve problems using these tools. These examples that I show you, apart from the one I used for the Campbell diagram, are real examples, so they refer to real designs. So depending on your design, KISSsoft could help in solving any dynamic issues in there. There is another question if we have a specific comparison between real test and simulation, and if it's possible to define unbalancing grade of a disc or shaft. So unbalancing grade cannot be defined. A direct input of an unbalanced mass should be defined. That way the whole input or the whole can be more general and have a specific value and not just a range of possible values. And regarding comparison between test and simulation, there are some available, and yeah, we can discuss further about them. There is another question if we can calculate the absolute noise level directly. The answer is not directly from vibrations at the moment. This is something that we would like to go to. For the moment, we don't have any direct connection between vibrations and noise. As far as I know, there are some approximate formulas regarding noise from gears directly, but not taking into account the dynamics of the whole system. Regarding if somebody can get this presentation, you can find that already in the download area of this web seminar tool as a PDF document. Regarding, there is another question that KISSsoft is calculating contact analysis as quasi-static, and how I can evaluate these results with reality. Contact analysis, the way we do it is actually quasi-static, and all our calculations are actually quasi-static. So for the forced response, what we do is we take a snapshot of the whole system after it has been calculated statically, and then we use constant stiffness for the dynamic response. So at this stage, we don't take into account any stiffness variation in the gear mesh. This could be also another excitation, dynamic excitation force, this change of stiffness. This is also something that we plan to apply in future releases. regarding the validation of, there is another question about how the mesh stiffness calculated with the contact analysis can be validated. This is based on the basic contact analysis calculation of KISSsoft, and this is validated thoroughly as a separate module, as a separate contact analysis module. There is another question about if vibration of the housing can be calculated. The answer is no here, so we don't take into account the dynamics of the housing. We have in cases the option to take into account the housing, but only in static calculations. An option would be to just use this static stiffness also in dynamic calculations, but we didn't want to do the simplifications because for dynamics of the housing, it's better if we have the modal stiffness and the modal mass and not just the static stiffness. So for the moment, we don't have that available, but this is something that we are planning to do. Another question is when we did the force dynamic analysis, we entered damping for material and bearing. However, in modal analysis, these are calculated from the internal geometry of the bearing. Actually, what we calculate from the internal geometry of the bearing is only the stiffness. So damping, if it is to be taken into account, it is to be entered by the user. So no damping is calculated by KISSsoft. And during modal analysis, damping is ignored. So we are talking about undamped vibrations for modal analysis. There is another question if somebody can generate bearing properties for hydrodynamic bearings, hydrodynamic sleeve bearings. There are some hydrodynamic elements available in KISSes, and you can use them to calculate some basic properties based on standards, and then you can have a constant stiffness out of that for your dynamics. And then there is a last question if the calculation is applicable also for plastic gears. So whatever is calculated in KISSsoft can be also used in the dynamic analysis of KISSes. So we will take into account during the dynamic analysis the stiffness that is calculated for the plastic gear specifically. So whatever stiffness is calculated for the gear mesh stiffness of plastic gears, this is taken into account then in the KISSes calculation. So I think that answered most or all of the questions. If there are any more questions, please keep on sending them. This will be tracked down, and I will just reply to them with an email to whoever sends it. At this point, I would just like to thank you once more for your attention and being present at this presentation. I hope you found it useful. We are always at your disposal for any kind of help or support we can give. Thank you once more. Bye from Bubicon. Bye. Thank you.